Dear learners, I welcome you all to this module. The title of the module is Division Algorithm, Divisibility and Euclidean Algorithm. In this section, we are going to introduce the division algorithm, which is the process of verifying the division, and then we are going to discuss one of its application called the base B representations. Later on, we are going to go through the concept of divisibility and some of its important properties. We are going to conclude this section by defining the GCD and LCM of two integers and the method called Euclidean algorithm to find the GCD of two integers. Now, we shall start the division algorithm. We started to learn mathematics by counting and then started to do operations. The ways that numbers are combined to make another ones, that is new ones. We know how to add two real numbers a and b to obtain the sum a plus b, and we learn to multiply two real numbers a and b and obtain the product ab. The third operation, subtraction, is defined in terms of addition by the rule a minus b is equal to a plus minus b. Another well-known operation is division, as we know. In this section, we are going to learn division algorithm, a method to find one of the dividend, divisor, quotient or remainder when the other three of these are already known or given, and to verify whether the division performed is correct or not. Before starting division algorithm, we can discuss the properties of real numbers, which helps to prove our upcoming theorems and results. We learned earlier that real numbers have a definite order. Later, we met the symbol less than or equal to, whose properties are summarized by saying that it is a partial order, that is, the binary relation less than or equal to is reflexive, that is, a is less than or equal to a for all a in real numbers. And then antisymmetric, if a is less than or equal to b and b is less than or equal to a for all a and b belong to real numbers, then a is equal to b. Next, transitive, when a is less than or equal to b and b is less than or equal to c for all a, b, c in the set of real numbers, then a is less than or equal to c. Look at this inequality, minus 10 is less than or equal to minus 7, that is less than or equal to minus 1 by 2, that is less than or equal to minus 0.5, that is less than or equal to 0, less than or equal to 1, less than or equal to 3.14, less than or equal to 4. In the above inequality, except for minus 1 by 2 less than or equal to minus 0.5, less than or equal to sign in the preceding list could be changed to the strict inequality less than. The basic mathematical operations, addition and multiplication, satisfy a number of important properties. We shall discuss the properties now. Let us take a, b, c to be real numbers. Then the first property is closure. A plus b and ab are both real numbers, that is closure property. Second one is commutativity, that is a plus b is equal to b plus a and a b is equal to b a. Third one is associativity, that is a plus b plus c is equal to a plus b plus c and a b multiplied by c is equal to a multiplied by b c. And the fourth property is identity, a plus 0 is equal to a and a multiplied by 1 is equal to a. And the fifth one is distributivity, a multiplied by b plus c is equal to ab plus ac and a plus b multiplied by c is equal to ac plus bc. And the sixth one is additive inverse, that is a plus minus a is equal to 0. Seventh one is multiplicative inverse, that is a multiplied by 1 by a is equal to 1 if a is not equal to 0. And the next property is when a is less than b, that implies a plus c is less than b plus c, and a is less than b and c is greater than 0 implies AC is less than BC. Next property is when A is less than B and C is less than 0, that implies AC is greater than BC. The last of the three properties relates to order. A set of real numbers may or may not have smallest element. For example, the smallest element in the set that is considered here is 1 by 2, 1 by 3, 1 by 4, 1 by 5. So, the smallest of the element belonging to the set is 1 by 5, and there is no smallest element in the set 1 by 2, 1 by 3, 1 by 4, 1 by 5, and the element goes on. But the case of natural numbers is little bit different according to the well ordering principle. We shall see about well ordering principle now. That states every non-empty set S of non-negative integers contains the smallest element. As we continue the section, we concentrate mainly on integers. All the properties of real numbers we listed about addition and multiplication hold good for integers in most instances because they hold for all real numbers. But the only one exception is the closure property, which simply states that the sum and the product of integers are integers. That is, the integers are closed under addition and under multiplication. But it is not the case. Not all integers satisfies closure property. If we take the set of odd integers, it is not closed under addition. For example, 1 and 5, both 1 and 5 are odd integers, but 1 plus 5, that is 6, that is not odd. Whereas, we can see that the non-negative integers is closed under addition and multiplication. If we ask to divide 59 by 11, we usually do as follows. So, we divide 59 by 11, we are getting the quotient to be 5 and the remainder to be 4, which means here the quotient is 5 and the remainder is 4, and we can write 59 as 5 multiplied by 11 plus 4. Here 59 is equal to 4 multiplied by 11 plus 15. This is also true, and we can write like this in many more ways. But in the case of division, we consider the remainder to be the least, that is, it should be less than the divisor. Now, we are going to prove that this sort of division is always possible, and moreover, the quotient and the remainder are unique. Suppose an integer a is divided by a positive integer b, we get a unique quotient q and a unique remainder r, where the remainder satisfies the condition 0 is less than or equal to or less than b. Here a is the dividend and b is the divisor. Before seeing some examples, let us see about division algorithm. The statement of the division algorithm is let a and b are two integers and b is greater than 0, then there exists unique q and r belonging to the set of integers satisfying a is equal to qb plus r, that is a is equal to q multiplied by b plus r, where r lies between 0 and b, 0 less than or equal to r less than b. So, now we shall prove this algorithm. First part, we are going to prove the existence of such q and r, and then we are going to prove the uniqueness of it. So, let us consider the set S. We are going to construct S that contains collection of elements of the form a minus xb, where here x is an integer and this a minus xb should be greater than or equal to 0. We are going to construct a set like this, and we are going to prove this set is a non-empty set. So, first let us take an element a, then that to be greater than or equal to 0. So, let a is greater than or equal to 0. In this case, I am going to choose my x to be 0. So, here a minus xb is equal to a minus 0 multiplied by b, that gives me a, that is greater than or equal to 0, which means definitely a belongs to S. Therefore, S is non-empty. Maybe if you consider the next case, if a is less than 0, then if you consider the modulus of a, that is equal to minus a, this will be positive. Since a is negative, minus a would be positive. Therefore, mod a multiplied by b is greater than or equal to mod a, and if you substitute minus a in the place of mod A, we get minus AB is greater than or equal to minus A. So, if you multiply here both the sides by minus 1, the inequality will get reversed. That is, AB is less than or equal to A. Therefore, since AB is a smaller quantity than A, if you subtract AB from A, the quantity that you are gonna have, that would be greater than 0, which means that A minus AB will be there in my set S. Therefore, S is definitely non-empty. So, A is already known to us. If A is positive or 0, then we have an element belonging to the set S, that is A, and if your A is negative, then also you have an element A minus AB belonging to the set S. Therefore, in all the cases, our S is non-empty. Since S is non-empty, by well ordering principle, this set will be having a least integer or least element. Therefore, I am going to take the least element to be R belonging to the set S. There exists X is equal to Q. I am going to have R to be of this form, R is equal to A minus QB. So, here A is equal to QB plus R, and R is greater than or equal to 0 because R is there in my set S. Therefore, now here we proved that the existence of Q and B. Now, the existence of R and Q we proved here. A and B are already known to us. Now, we are going to prove the R that we obtained from here, that would be less than B. So, suppose what happens if my R is greater than or equal to B? If R is greater than or equal to B, then R minus B will be greater than or equal to 0. Let us consider my X to be equal to Q plus 1. Now, A minus Q plus 1B is equal to A minus QB minus B. So, this A minus QB is what? A minus QB is R. Therefore, I am going to substitute here. This is R minus B, and R minus B is greater than or equal to 0 because that is what we assumed here. So, since R minus B is greater than or equal to 0, I am going to try to put this R minus B of the form A minus XB. That is, if you consider A minus Q plus 1B, that will give you R minus B. This since R minus B is greater than or equal to 0, this R minus B will be there in my set S. But what about R? R is the least element belonging to the set S. R minus B is an element that is less than R. If you get R minus B also belonging to the S, then it will lead to the contradiction, to the fact that R is the least element of S. Therefore, definitely our assumption is wrong. Therefore, R should be less than B. So, now till this we proved the existence and the R is less than B. Now, we are going to prove the uniqueness of it. Now, what happens if you are able to express the same A in two different forms, that is A is equal to Q1B plus R1 and A is equal to Q2B plus R2, where Q1, R1, Q2, R2 are all integers and 0 less than or equal to R1 and less than or equal to B less than B and 0 less than or equal to R2 less than B. What happens if you have like this? So, now since both are A, we can equate them. I have Q1B plus R1 is equal to Q2B plus R2. From here, I am getting R1 minus R2 is equal to Q2 minus Q1 multiplied by B. So, that also implies modulus of R1 minus R2 is equal to modulus of Q2 minus Q1 multiplied by B, where B is already greater than 0. So, now we know that both R1 and R2 lies between 0 and B, that is 0 less than or equal to R1 and R2, that is less than B. That gives us 0 less than or equal to R1 less than B and minus B is less than minus R2 less than or equal to 0. So, I have multiplied the second inequality by minus, therefore, the inequality gets reversed. So, from here I am getting this R1 minus R2 lies between minus B and B, that is minus B less than R1 minus R2 less than B. Therefore, if you take modulus of it, that is modulus of R1 minus R2 is equivalent to modulus of Q2 minus Q1B. From here I am writing here Q2 minus Q1 multiplied by B, that will be less than B, because we are multiplying something, a positive number with B, this quantity will be definitely less than B. That implies that modulus of Q2 minus Q1 will be less than 1. Therefore, since we have Q2 minus Q1 is greater than or equal to 0 and we have Q2 minus Q1, the modulus of it less than 1, the only one possibility is modulus of Q2 minus Q1 should be equal to 0. So, if this happens only if Q2 minus Q1 is equal to 0, that implies that Q2 is equal to Q1. If this is the case, if you trace it back, you will have R1 is also equivalent to R2. So, even though we express in two different forms, both are same. So, now this proves the uniqueness of the algorithm. So, here we proved existence and the uniqueness of such Q and R satisfying A is equal to QB plus R, where R lies between 0 and B. Next, we are going to see a corollary based on this algorithm. That corollary says when you have two integers A and B is not equal to 0, there exists unique Q and R belonging to the set of integers satisfying A is equal to QB plus R, where 0 less than or equal to R less than mod B. The difference between this corollary and the division algorithm is, while in the division algorithm we have had this B to be a positive integer, that is B is greater than 0. Now we are not restricting that B, we are allowing B to take negative integers also. Now you have to note that B should not be equal to 0. So we are going to prove this corollary in two different cases. The first case is what happens when the B that you have considered is already positive. If it is already positive, you don't have to worry about it. From the division algorithm, this will be true. So what happens if B is negative? If B is negative, consider modulus of B. This modulus of B will be positive, that is modulus of B is equal to minus B. So now, this algorithm with division algorithm that we have considered, that would be true for this modulus B. Therefore, you can write for that, you can find a unique Q1 and R satisfying A is equal to Q1 mod B plus R, and replacing mod B as minus B, you have A is equal to minus Q1 B plus R, where 0 less than or equal to R less than modulus of B. So, here you can note it down. You can take this minus Q1 as some quantity Q. Q is an integer. So, you can take this minus Q1 as Q and you can write A is equal to QB plus R, where 0 less than or equal to R less than mod B. So, we are able to prove the corollary for this case also. Next, we shall see an example. Now, here our A is 24 and our B is 5. So, we are going to express this A and B, or we are going to find unique Q and R, so that I can write A is equal to QB plus R. So, now here I have 25, that is A, and I have 5. Now, consider A minus R is equal to 5Q. How did I arrive at this? This is A minus R is equal to BQ. So, now I have substituted the values 24 minus R is equal to 5Q. Now, we have to find this R in such a way that if you substitute R here, you have to get a multiple of 5. So, the possibility is R should be equal to 4, and so now therefore, R is equal to 4. If you substitute here, you have 20 is equal to 5Q, that is Q is equal to 4. Now, we can express this 24 as 4 multiplied by 5 plus 4. So, you can see here, you can follow the same method to write any two integers in this form. Even if you have a very big number like 479510 and 6782, you can do in a similar way and you can find a quotient as well as the remainder. Here the remainder is 4770 and the quotient is 70. You can do in this manner. Now, we shall see a definition. If A is equal to QB plus R with 0 less than or equal to R less than modulus of B, then Q is equivalent to floor of A by B if B is greater than 0, and the same Q is equal to ceil of A by B if B is less than 0. We shall see an example. If A is equal to minus 547 and B is equal to 13, then we have CL of A by B is equal to minus 547 divided by 13, that gives us minus 43, that is equal to Q. Now, it is straightforward to determine R. R is equal to A minus QB, that is equal to minus 547 plus 559, that is equal to 12. Thus, minus 547 is equivalent to minus 43 multiplied by 13 plus 12. So, this way we can write. And then we shall see one of the application of the division algorithm, that is representation of integer in base B. One of the application of the division algorithm is to convert a decimal integer to any other base. We use decimal notation or base 10 representation in our everyday life to represent any real number. For example, the decimal expansion of 4521 and 45.21 is given here. That is, 4521 can be written as 4 multiplied by 10 cube plus 5 multiplied by 10 square plus 2 multiplied by 10 plus 1 multiplied by 10 power 0. And the same 45.21 can be written as 4 multiplied by 10 plus 5 multiplied by 10 power 0 plus 2 multiplied by 10 power minus 1 plus 1 multiplied by 10 power minus 2. Some of the important representations are binary representation, that is base 2 representation, and then octal representation, that is base 8 representation, and then hexadecimal representation, that is base 16 representation. Any positive integer can be chosen as the base. The following definition helps you to learn how to represent any positive integer in base B notation for B is greater than or equal to 2. That is, given a fixed natural number B is greater than 1, the base B representation of a natural number n is the expression an minus 1, an minus 2, etc. a0 to the base B, where a0, a1, etc. an minus 1 are those integers with ai lies between 0 and b, that is 0 less than or equal to ai less than b, and n can be written as an minus 1 multiplied by b power n minus 1 plus an minus 2 multiplied by b power n minus 2 plus etc. a1b plus a0. Thus, we have an minus 1, an minus 2, etc. a0 to the base b is equal to an minus 1 multiplied by b power n minus 1 plus an minus 2 multiplied by b power n minus 2 plus etc. plus a1b plus a0. Dear learners, we have come to the end of this module. In this module, we introduced the division algorithm, which is the process of verifying the division. Then we discussed one of the most important application of division algorithm, that is base B representations. I hope this module will be very useful to you. In the next module, we shall discuss about the concept of divisibility and its properties, and GCD and LCM of two integers, and the method to find the GCD of two integers, that is Euclidean algorithm. I hope that will be also useful to you. We shall see in next module. Until then, thank you.